Okay, we're back for day number 2 of the mean value theorem, starting with my example number 5, which is patterned after a lot of the things you'll see from College Board. This is typically made into a multiple choice question. They ask for 3 things, which ones must be true. Notice the word must is there. H is a function that is continuous. Notice it says continuous, but notice what it doesn't say, which is differentiable, meaning that this thing can have corners, cusps, vertical tangents, and the like. So I'm going to make a quick picture of it. This will be my own picture. I don't really know necessarily what's going on, but that's okay. Here's an x and a y axis. H is going to go through the points 2, -3. All right, so we'll just fake it. Here's 2, -3. 5, 9. It's going to be way up here. 5, 9. Obviously not perfectly to scale. And then finally 7, -3. So we're back down to level with the bottom here. See why I'm not an art teacher. All right, let's connect this and make a graph called h of x. It has to hit these points, but nobody said that this is a minimum, so I'm going to go below it and kind of come back up. Again, a lot of students think that 5, 9 is the max. It's not. We just have to go through it. That's all. All right, so there's a sample problem or sample graph. All right, let's see which of the following must be true. Number 1, the function has at least 2 zeros. That is, it crosses the x-axis at least 2 times. This has to be true, because if you're going from a height of -3 to a height of +9, there has to be an x-axis crossing because 0 is between them. Same thing, you're at +9 here, you're coming back down to -3, you had to cross again. So that is intermediate value theorem. That's what they're testing there. That must be true. It's a theorem. It's true all the time. So number 1, definitely. Number 2, Roman numeral 2, the graph of h has at least 1 horizontal tangent. Here in my drawing, there are 2 of them. There's one here and there's one here. It would seem to be true, but it doesn't have to be. And the reason why is because, again, as I pointed out before, we know the function's continuous, but we don't know that it's differentiable. What if we had something, say, like this instead? Maybe the graph goes like that. Now there are no horizontal tangents. Sure, there's a max and a min, but this is not a horizontal tangent here. Who's to say that the tan line doesn't go like that or like that? All of those hit once at 5, 9. So this does not have to be true. And then finally, part C, between 2 and 5, so in other words, between these 2 dotted lines here, h of c, in other words, the height of the red graph must be 4. That's true, that's IVT once again, because y equals 4 would be, again, a horizontal line, and 4 is certainly between 9 and -3. So yeah, that has to happen. So number 5 is 1 and 3 only. Now, if you took the same problem and just simply changed one word from continuous to differentiable, obviously 1 and 3 would have to stay true for the same reason, IVT. But now that it's differentiable, you can't have corners or cusps like I had in this other drawing. They have to be smooth. The function has to be smooth and curvy. And so therefore, this will also be true. So if it's differentiable, then yeah, all 3 are correct answers. So that's the difference. A lot of having success on the AP exam is really being able to be good at vocabulary and be willing to really read. The devil is in the details, as they like to say. All right, moving ahead, number 7. Again, I patterned this similar to what you might see on a free response question from the College Board. It's my own, but it's inspired by them. A car travels on a straight road. You've got the velocity and the acceleration at certain points in time, written down. It's obviously not the whole motion of the car, just a couple snapshots, a few snapshots. And part A says, hey, somewhere between 0 and 5 hours, Does there have to be a time? Must there be a time when the velocity is 35 miles per hour? Justify your answer. And looking at the chart, I'm going to say yes. And the reason why is because you were at 25 miles per hour when the story started, and half an hour later you're going 40. Since this is a car traveling on a straight road, obviously it has to be continuous. It has to be differentiable unless the car is suddenly going from drive to reverse. Nobody drives like that. So regardless, IVT guarantees that somewhere between 25 and 40, somewhere between 0 and half an hour in, you had to be going 35 miles per hour because 35 is between 25 and 40. So I'm going to write that out in a nice sentence that College Board will be thrilled with. I'll do that right now. So absolutely, yes, 35 is between 25 and 40. Therefore, the intermediate value theorem, IVT, is fine to write. Guarantees that, the velocity is going to have to be 35 at least sometime, at least once, between the start and a half an hour in. So definitely yes. Mention IVT. You're good to go. Okay, part B of the same question says between 0 and 5 hours, must there be a time when the acceleration is 0? Justify your answer. And at first glance, you're like, whoa, look, the acceleration's positive the whole time, so no. But I have to say, how do you know the acceleration's positive the whole time? Just because those 6 numbers that happen to be in the chart are all positive? Who's to say it doesn't go negative in between? I mean, right here from 2 to 4, you haven't done any observation of this car in 2 hours. What do you know about what happened? The answer actually is yes. There must be a time when the acceleration is 0. That's a definite yes. At first, that's sort of surprising to me. The reason why it's yes is the mean value theorem this time. And here's what I'm drawn to. I see a pair of 40s right here. One is a half an hour in, the other's 4 hours in. If you think about this, you've got the velocity at 4 hours minus the velocity a half an hour into the car trip over time, which is 4 minus a half. Since these velocities are both 40, you're going to have 40 minus 40, which is 0. 0 over who cares, 3.5. So if the average velocity in this green time interval is 0, then the derivative must also be 0, and the derivative of velocity is acceleration. So yes, the acceleration must be 0 at least once, according to the mean value theorem. So let me write that out. So again, I want to answer the problem. I want to actually say yes or no. So the answer is yes. I want to show what College Board refers to as the difference quotient, a pair of subtractions with a fraction bar. And then I also need to mention mean value theorem, at least mention it by name. If I don't mention it by name, I have to explain what it is in detail. It's easier to mention it. And there's really one more thing I should have said, and that is that acceleration is equal to the derivative of velocity. I said that when I was talking to you guys. I should write that as well. That allows me to claim this for sure. All right, there it is. Nice. Okay, one more slide. We've done the intermediate value theorem. We've done the mean value theorem. And finally, last but not least, the extreme value theorem. Honestly, it probably is least. It's the least used of the three. It's still a theorem, so it's still true all the time. What it says is if you have a function that is continuous, it doesn't have to be differentiable, just continuous, on a closed interval all the way from A to B, then this function has to have an absolute max and an absolute min. It just has to happen. So let's test it out. Part A of example 8, you can see that this function is continuous. It bends right there, comes back over to here, and ends. All right, so in this case, the A is the -2, the B is +3. It is continuous the whole way between -2 and +3 on the x-axis. So it must have a max and a min. What are they? Well, the max, remember, max and min values are the y-coordinates, not the x's. So there's a maximum of 8 that happens at point -2, 8. And there's a minimum value, and the min is -1, and that happens right here at +1, -1. Okay, so that's the extreme value theorem in use. Notice that the maxes and mins can either happen at endpoints or at critical points when the derivative is 0. All right, part B. Let's see, this is clearly a min right here. So we have the min being -6. And then the max, oh no, wait. The max should be +6, but there's a hole there. And I can't claim that the maximum value is 5.99 because what if my friend says 5.993? And then I say 5.994 and someone else says 5.999999, and we get into this unwinnable war of who can be the most obnoxious and say the most nines. And so there is no max. There's no absolute maximum value. Which makes me say, wait, I thought this thing was supposed to be a theorem. How come it failed? And the answer is it didn't fail. It just simply didn't apply here. The extreme value theorem says if the function is continuous, well, there's discontinuity here, so you can't use the extreme value theorem. So there doesn't have to be a max and a min. There was a min, there is no max. So that's it. We learned the mean value theorem. Did a lot of examples. We briefly learned the extreme value theorem, more on that later. And we went back and also reviewed the intermediate value theorem, or the IVT. So, nice job. We'll see you next time. Take care, everybody.